Alright, hey everyone, it's me, Neil again. Most of my talks start with a big long introduction section where I talk to you about who I am and try to get some demographics out of who's here so that I know which bits I can skip because you already know it. Who I am, this is my third UQCS talk for the year and I think I gave 4 or 5 last year. If you don't know me and you want to, please by all means come chat afterwards, but yeah, I'm Neil. As for student knowledge, most of this isn't taught at UQ at all. Well, the first bit is in 2310, but from there it's going to be all fresh content, so yeah, we'll just get straight into it. From containers to clusters. So what we're going through here, containers are a sort of industry standard tool in a lot of places that you use to isolate environments and stuff. It's hard to know until you know what it is. Clusters, a bit more obvious, it's the big warehouses full of computers that places like Google and Apple and Amazon all have. And it turns out if you want to have a big warehouse full of computers, you can't plug a keyboard into them one at a time to debug stuff and turn them on and off again. And this is how you make that work if you're operating at that sort of scale. Quick disclaimer, I've never personally operated at that sort of scale. Most of this is just research and looking into the papers published by the people that do this. But it's cool stuff, so we'll get into it. So first, taking a couple steps back, some prerequisite knowledge. What is an operating system? Or, well, an operating system's a bunch of things. It handles making sure your system's secure. You can think of it as the layer between the code that you're running and the actual physical hardware that it's running on. It's in between those two and mediates things. The operating system handles file systems, it handles drivers for weird devices, handles scheduling. If you've got multiple programs running on a single core computer, what's going to happen? And in general, it just does an abstraction. Operating systems are pretty complicated things. At the moment, though, we're looking at a particular part of the operating system called the kernel, which is like the root main part of the operating system that does all the serious stuff. And basically all of its jobs can be summarized into answering questions. In particular, answering 2 types of questions, which are system calls or syscalls and interrupts. Syscalls are questions that code asks the kernel, and the kernel provides a response. Things like, what's in this directory? You make a syscall, the kernel responds, you know what's in that directory now. Send a signal to a process, send a packet through the Ethernet cord to the next computer, please. I would like to view a website. All of that sort of stuff happens as system calls, which are, for all intents and purposes, basically just C functions. You call the function, the kernel does some stuff, and it gets back to you with an answer. Generally, that stuff will involve possibly interfacing with hardware, doing some security checks, but it can all be broken down into an answer to a question. The other types of questions are interrupts, which are questions that the hardware asks the kernel. So it's not a function that you call, it's something will happen, and the processor will say, wait, hold up, I'm not sure you're allowed to do this. Let me just check with the kernel first. And so it still is a question. It's, can my process have CPU time? You're trying to use the CPU and the CPU says, wait, is this allowed? Let me check with the kernel. Or you're trying to access some memory and it says first, got to check that's allowed. You can't just access memory you're not allowed to access. And so all of these still come under the general gist of a question. Something asks a question, the kernel provides a response, and from that, programs work. Right? And most functionalities in an operating system can be broken up into syscalls and interrupts. The fun bit is, what if the kernel lies? Right? If everything you do as a kernel is just answering questions, how important is the truth to these questions? Or what could happen if you tried bending the truth? Things like, we come up with a syscall. Can I send a signal to a process? And the kernel says, what process? I've never heard of that before, it doesn't exist. I mean, it might exist. You don't really know because your only way of finding out if it exists is, again, asking the kernel a question. If the kernel's dedicated towards lying to you, you can't really tell what's going on. Things like, can I read this folder? Which, for those who don't know, that's the folder that has everyone's usernames and hashed passwords on a Linux system. Generally, if someone reads it, that's considered a bad thing because they can try to guess your password now. Simple, you ask to read the file, and the kernel says, no, never heard of it. You can't really check that. Your program can't look at the file system directly because everything goes through the kernel and through these question-answer interfaces. So if it lies to you, you just have to believe it. Similarly, one more example, can I send a network packet through EN0, which is typically the 0th or 1st Ethernet interface on the motherboard. Can I send a packet through there? I would like to visit this website, please. No, you can't send a packet because we're not connected to the internet. Again, as a process, everything that the process tries to do to the hardware, you've got the kernel sitting in between, monitoring and basically defining what reality is for the perspective of the process, right? Any lies that the operating system or the kernel tries to tell you, you can't go around the kernel and ask someone else. So essentially the kernel is the single source of truth of what is reality for a process, right? Which you can do a lot with that, right? I mean, for a start, you could just have a kernel that lies to people and then break programs horribly. That is one option. But there are possibly some better applications of this. And the key one is sandboxing. So sandboxing is where you take an application and you put it in a little box, similar to a sandpit, right? In a kid's playground, can't get out. And the idea is they can play in the sandpit, they can have fun, they can't hurt anyone else. They can't be interfered with from the outside, they can't interfere with the outside world. And the reason they're not able to do so is because their entire interface to the outside world is dependent on the kernel telling them what the outside world is, right? And if you lie, well, they can't interfere with what they don't know about, right? So, how does this happen? I'll get to what all of that means soon. The kernel doesn't just sort of lie haphazardly based off what, rolling a dice or something, or how it feels on the day. There's structure to it, structured lying, and it's managed through a set of operations called namespace operations. Right, so there is a man page in the 7th category of the manual on Linux system called namespaces. This is all Linux specific stuff. Other operating systems have equivalents to it, but the Linux one is what gets used most in practice, so we're going to be sticking with that. But the idea is, for a namespace, right, it's similar to a namespace in other programming uses of the world, like C++ or I think C# might have them. But the idea is, a namespace is a collection of, in this case, processes. And if you're inside the same namespace as another process, you can see each other, you can communicate with each other. And if you're inside a different namespace, it's like you're in an entirely separate world, and you can't interact at all. Right? So there are seven types of namespaces on a Linux system. Right? So each of those namespaces, you can be in network namespace 1, but PID namespace 2, they're all orthogonal or unrelated to each other. But you can use various combinations of them to do different things to processes. Things like the network namespace, that controls which network devices you believe you have access to, right? So if you have a computer with an Ethernet cable and a Wi-Fi card, you can say, I want this namespace to only be able to see the Ethernet cable. And this namespace can only see the Wi-Fi card. And then every time you start a process, you say, which namespace do you want it to be in? And then once it's in that namespace, it only has access to it, only believes in the existence of the network device you've told it about. So these processes can only talk over Wi-Fi, these processes can only talk over Ethernet. More often what you'll do with this is you'll have These are the processes that can talk to the Ethernet device. These are the processes with no internet access. Or these processes have a virtual Ethernet connection, which we can then put a firewall in the middle of to make sure that only allowed packets go through. But you can take processes and you can group them out and give different groups different realities. Right? So networking is which network cards they have access to. The PID or process ID namespace is which processes they can see on the system. So if you start up PS in a terminal or your system task manager or something, you'll only see the processes that are running in your namespace. And process 7 in this namespace has nothing to do with process 7 in a different namespace. They are, for all intents and purposes, for PIDs, different computers. Right? The user namespace, each namespace has a different list of users, so they have a different admin account, different other accounts. Just because you're an admin account on the one doesn't mean you're an admin account on the other. So it's a good way if something needs admin permissions, you can say, yes, you are the admin. Not the admin of my computer, but you're the admin of this little world that we've trapped you in. So it's good for security. The mount namespace controls which file systems you have access to. So you can say, I don't want this process to believe that this folder exists. It's different to not giving them permissions because it doesn't show up as it's there but you're not allowed. It shows up as there is no folder. What are you talking about? We can't show you because it isn't there. Right? So the other three, IPC, C group, and UTS, aren't as important. So we're going to skip that. So how this works in practice is that when you turn the computer on, every process is just in the same namespace for each of the 7 types of namespace. Right, so you have all of your processes that are running, and then one of them you can pick. There's a syscall called unshare, which says I want to stop sharing my namespace with the rest of the computer. You pick which namespace you want to stop sharing, and then you get separated out. Now, when you first separate it, you still have the same starting conditions as the other namespace. Like you might still see the same network cards or still see the same file system. But when you start making changes, like remove this directory, unplug this device, it separates you from the other processes. So any change you make doesn't affect anyone else. Right? So the idea is you would create a process, split it out into its own namespace, configure that namespace however you want it, and then do that again for all of the other types of namespaces. And then you can start the program that you want to run in the secure environment. And it's in its own world, or its own 7 worlds, where everything is finely tuned for exactly its needs, and it doesn't affect anyone else. This is not an easy thing to do. So configuring a namespace, you need to call a C function, you need to error check that function. Then there's the question of setting up the new namespace to be exactly how you like it. That's more work. Really, we don't want to be doing this every time we run a program in a secure environment. And so we come up with other solutions, which take this isolation or sandboxing thing and make it more accessible. The main thing that does that these days is Docker. It's the little whale with the shipping containers on its back. Other things are Rocket, which is like a clone of Docker that's very similar. And then LXC, which is the Linux container framework, which is not a full-fledged solution to this problem. It's just a library that you can use to make it easier to do, that bundles some common actions together. Anyway, so next up, before we get into how these work, is why do you want to do this? Right? And it basically comes down to 2 reasons. The first is security. You want to make sure that this program can't mess with any other program. Say if you're running a website and you've got a server set up, if someone, heaven forbid, hacks your server and breaks into it and gets it to do what they want it to do instead of what you want it to do, you don't want that person to have full access to your entire computer. It'd be great if they couldn't get access to anything, but if they have to get access, you would like them to get access to a small subset of things, right? You could solve this by just putting each server on its own separate physical computer, and it gets expensive. The other advantage is stability, right? So something that comes up a lot in software, and this may have happened to you, is what's called a works on my machine class of bugs, which is where you run your code and it works, and then you send your code to another developer, or you send your code to the production server, or you send your code to the tutors to market, whatever you want, and they run it, and they say, well, no, it doesn't work. Your code doesn't work. Why? But as far as you're concerned, it does work because you ran it and it was fine. So something about your computer versus the production server versus your friend's computer versus the tutor's computer, something about those two environments is different. And as much as we'd all like to be writing perfectly portable code, a lot of the time having differences in small amounts of your operating system can just break things. Right? If you're using external libraries in C or Python or something, then which packages you have installed on the system could make or break whether your application is able to function at all. Right? Which is what we want to avoid. So we care a lot about stability, and the easiest way to make sure that your application runs the same way every time you run it on every machine that you run it on is to just always run it on the exact same machine. Right? I don't mean take my MacBook Pro and just connect it to the production server and hope for the best. But the idea is, if we can, using containers or using structured laying or whatever, convince the application that it's always on the exact same computer, then it's always going to run the exact same way. So things like that mount namespace, where within that namespace you can have an entirely different file system to the rest of the computer, that can be really useful because you can put an application in a namespace and say, I'm going to create this namespace, I'm going to take away my current file system, and I'm going to put in the file system of the computer that I know my code works with. And then when you start running your code's running, as far as it's concerned, in the exact same environment. The same files are there, the same packages are installed, same operating system, the same version of that operating system. It's all effectively the same, because as far as the application can tell, if it tries to say, open a file to read what version of the library it has, the kernel's just going to tell it whatever file that you asked it to tell it earlier. So you'll always be on the same, essentially on the same operating system and the same computer, but in a portable now, where you can run the application all over the place, and it'll just always think it's on the same computer. So you get this stability, right? And then the fun bit, and where Docker comes in, is that if you've got this description of the computer that my code works on, you can save that to a file. You can send it to people. You can make a backup of it so that if you need to start the application again, you can do that. Right? And so what Docker does is it takes this stability, this definition of the one computer that my code works on, and it puts it in a file. And you can send that file around. You can save that file and you can upload it for other people to use. And that's pretty much what they do. So in Docker terminology, this is called an image, a Docker image. And it's a name and then a version number, or a tag more generally. But you can say, I want to run Postgres. I don't want to decide what operating system to run Postgres on. I don't want to have to configure a Postgres database because that's really hard to do. I don't want to set up all the security rules of Postgres, install all of Postgres' dependencies. And then when you finally get to the end of that, have it still not work because Postgres is a little bit fiddly. Instead, someone, probably the people who wrote Postgres, have figured out this is the type of computer that Postgres will work best on. You start with a Debian installation, you install these packages, you put the Postgres binary here, and it'll work. And so they take that Docker image, and they upload it online. You can just download it and say, run me a Postgres, please. And it'll run Postgres in the exact same computer and configuration that Postgres is always used to running in. And so you don't have to worry about any of this will it work on my machine bugs. It also means that if you want to uninstall it, you can just delete the entire image, which is much nicer. Other things, you can make Docker images for operating systems at particular versions so that you can just run, I want to see what Ubuntu would do in this situation. You don't have to clean install your operating system. You can just have a Docker image for Ubuntu. Alpine is another pretty common one. It's a Linux distribution that's built to be as small as possible. These things are files and you're sending them around. You don't want to be sending out the whole 3 gig of Ubuntu every time that you want to start a server. Alpine's a smaller base image that you can start with. But anyway, we can build images. Images are cool. They're a way of locking in everything that we want to care about in our program so that it's always the same and stable. And we can actually make our own. So what happens, this is very Docker specific, though I think Rocket will do it too. You can write what's called a Docker file with just a bunch of lines saying, this is how you start with an existing image like Ubuntu, and how you make it into an image that will run my code. Right? It's a file, you can version control it, you can have automated tests for it, and it will spit out a Docker image that will always run your code, always on the same machine. So the dev has this Docker file, they build the Docker image, they run the code. The other dev, or the tutor, or the production environment, has the same Docker image. So you don't get this, is it working on my machine anymore? It's just, this is the machine the code runs on. And that's a version control part of your application. And so it's always going to run in the same environment and always hopefully work. Maybe, have to write good code first. But, so what happens, you start with where you want to, your base image or operating system generally, and then you can run commands. So you could, you could do this without Docker. You could say, if I want to run my application, I will fresh install Ubuntu 18.04. I will open up the terminal and I will install the Java runtime environment. And then I will copy this jar file from, I don't know, USB or something into this folder. And then when I want to run my application, I will run it with this command. But instead of physically doing that to a computer with a keyboard and terminal, and possibly USB or something, and having to plug in a monitor, we chuck those 4 lines into a Docker file, and we say, Docker, build my image, please. And it will just spit out a Docker image file, which you can copy around, download on servers, run, and it'll build your app in that environment, exactly the way that you want it to run. Right? And so when you run your image, it will do all the namespacing stuff, separate it out into its own environment, its own network, its own firewalls, its own file system, which is this, its own users, groups, process namespace so that it can't mess with the rest of your system. And that whole bundle of things is called a container. So you can take an image that you built, or an image that you've stolen from the internet, or an image that you've legally downloaded from the internet rather, that would be more appropriate. You can take a Docker image and you can run it and you can get a container. And the cool bit is that if you run it a bunch of times, you will always get the same container that runs in the same way and that's repeatable and less likely to have an individual, but my machine works sort of bugs. All right? Everyone following with this so far? So this process, images, containers, and stability, is basically all there is to know about containers. I mean, there's more. You can obviously research more. You can read the functions on how you could actually build these yourself. But those are the key concepts. The only other things is that when you run a container, you can give it some extra information, like I want this container to have access to this folder on my file system, or I want to run it with these environment variables. But the idea is still the same. Doc is the main one. And how do we get from there to clusters? So what I've got here is the logo for Kubernetes. Kubernetes is a lovely open source program by Google that is a cluster orchestration program, right? So that's a mouthful, but what it is it takes a cluster of computers, whether that's the 3 cheap virtual private servers that I'm renting off of GCP, or it could take a warehouse full of computers, like physical computers with cables between them. It'll take a bunch of computers and it will get them to operate together in a cluster, right? And so what happens with this is instead of interfacing with a bunch of computers, like if you say, I want to run my code, you no longer have to go to 30 computers and run your code. Instead of interfacing with a bunch of computers, you're interfacing with a cluster. And so you don't talk to the servers, you talk to Kubernetes, and Kubernetes talks to the servers for you, right? And the way these work, the way that people have deemed to be the least effort to deal with them, is you give Kubernetes or the other competitors a description of the environment that you want to have, right? So that could be something like, I want 3 databases, like all Postgres, all just working together, doing the replication or whatever Postgres does. I want 3 databases, and I want 12 Java applications that all talk to those databases, and I want Nginx in front load balancing. And then I want the users connected to Nginx. And you can say, that's what I want to happen. Here's a room full of computers. I don't care exactly what runs where, but I want it to look like this when it's finished. And you give that information to Kubernetes, and Kubernetes will make it happen for you, right? And it does that in quite a number of complicated ways. Kubernetes is a massive, massive program with a lot of effort and engineering going into it. But it basically comes down to these 3 things, right? So we're going to go through them one at a time to hopefully make it less scary. This diagram is from the Raft consensus protocol or algorithm, right? So that is, it's been recently invented, and despite what the diagram may have you believe, it was invented to be as easy to understand as possible for something doing this job. So what the problem it tries to solve is distributed consensus. If you have a bunch of different computers, or people, or nodes, or agents, or whatever you want to say, if you have a bunch of different processes that can each send each other messages that may or may not work, and you want them all to agree on the fact. So that fact, in this case, is going to be, what did the administrator say that the cluster was meant to look like again? Right, so you tell one of the servers that, it needs to get that information to all the other servers so they will agree. Basically, any data in the cluster needs to be consistent. And so this is an algorithm that will basically just make that happen. There's inside of Kubernetes, there's a big separate boundary where this is the distributed consensus algorithm, and this is the code that uses the distributed consensus algorithm, and there is a very clear line between them. But the idea is, I'm not going to go into exactly how it works. It's complicated. It's called Raft. If you want to look it up, it's pretty cool, but it is complicated. The idea is you give it information, and you give it a bunch of servers, and it will make sure that all of the servers agree on the information. Right? And that's part 1 of Kubernetes. Part 2, now I'm not a light control engineer, so if I drew this diagram wrong, please don't hate, is a feedback loop. Right? So coming into your feedback loop, we have the goal. This comes straight out of the Raft protocol. It's the information that the administrator says, this is what the service should look like. It's your big map saying 3 databases, 12 applications, 1 load balancer, and then the users connect to this, and the rest is all private. That all just comes in as a big old YAML file of data. That's the goal. And what happens is that Kubernetes will, on a loop, look at the current state of affairs. So if you say, I want 3 databases, it's going to look at the cluster and say, well, how many databases do we currently have? We currently have 0 because we didn't know we needed any. It'll find the difference there, which is we need 3 more databases. It'll do that. It'll create 3 databases. It'll measure that output, measure how many databases we have, feed it back into here again, say we wanted 3, we have 3, the difference is 0, we're actually okay now, and then it'll stop. And it'll do this in a loop. So say, for example, one of them dies for some reason. Whether the computer got unplugged and you no longer have access to that node, whether someone wrote a bad database that segfaults occasionally, whatever happens, a database has died. Kubernetes looks at the goal, we want 3 databases, looks at the state, we have 2 databases now because one of them's dead, takes the action, add a new database. And it'll just loop that constantly. What this means is if you change your goal, say now I want 6 databases, I'm getting more customers, it finds the difference, it adds the extra 3 on. And it'll just keep doing that forever to make sure that what's happening on the servers is what you asked it to happen on the servers. What this means is that you don't need to say, add a database. You never need to look at the current state of things, do that dipping in your head and say, I want to create this or I want to delete that. You just tell Kubernetes what you want the end goal to be, and it'll figure out the details for you. Now, if you have 3 databases or 6 databases or however many, that's not that hard to do that math yourself. But if you have a warehouse full of computers, you probably don't want to be saying start database in a loop for 50 times and then start application in a loop for 100 times or whatever. It's much nicer to just say, this is what I want. Please just make it happen. Right? With that, it'll do some little nice things like put the 2 databases on 2 different computers if it has enough computers to do so, so that if some hardware failure happens, it limits the effects of everything. And a bunch of other nice little best practice things that the people at Google figured out while building it. But so we've got a distributed consensus algorithm, which feeds into the goal of this feedback loop. And then the third part of the system is DNS, right? So DNS is a pretty common network thing. It turns a domain name into an IP address. What does that have to do with clusters? So a surprisingly common problem actually in making distributed systems or using microservices or whatever you're into is called service discovery, right? It's all well and good to say that I have 3 databases on this cluster. It's another thing in your applications code to say, please connect to the database now, right? So if you're doing it manually, you might turn the database on, check the IP of the server that you turn the database on with, and then run your application with an environment variable saying database URL equals or something. And you just plug that IP in manually. If the database dies and needs to be restarted, you'll need to turn your application on and off again with the new environment variable when you get the second database. Things get messier, right? So Kubernetes actually solves it with DNS. They have their own DNS resolver inside the cluster, right, which says, and every application that's trying to do a DNS query goes through the cluster DNS first. And that says, basically, if your domain name ends in .cluster.local, we're going to handle that query internally, please. I mean, if you're just trying to make a request to a third-party API, it'll just find out from the actual DNS server where to go. But yeah, if you're trying to do something in .cluster.local, it'll handle that. It'll use the internal Kubernetes state. Say, if you want to connect to Postgres service 1.cluster.local, that's not exactly how they structure the URLs, but it's pretty close. If you want to connect to Postgres service 1, it'll figure out which IP address that's running on, and it'll point you to it. It might also do a little bit of making a fake IP address out in front of all 3 Postgres clusters so that it can, all 3 Postgres servers so it can load balance them for you. It'll do some pretty fancy networking stuff on the inside. which gets neat in trying to improve performance. But the general idea is we go from connecting to things by just chucking the IP address in an environment variable to saying, I want to connect to this domain name, .cluster.local. And that will forward you to wherever you need to go within the cluster. And those three things together, along with probably millions of hours of engineering effort, makes Kubernetes. Right? So that's the general gist of how it works. You come up with what you want it to do, it'll make it happen. And then once it's made it happen, it'll connect to things inside that. So that's Kubernetes. Worth mentioning, people often abbreviate it to this if you're trying to Google stuff and you get sick of typing it out. Or if you're trying to Google stuff and other people are getting sick of typing it out and you're like, what is this? Eights? K8S, whatever it is, that's also Kubernetes. They just took 8 letters out of the middle. Similarly, and this freaked me out to think about it, but internationalization, I18N, it's the number of letters they ripped out of the middle, which scary that words get that long, but here we are. So, next up I'm going to walk through the basics of how to use Kubernetes. Now, I have actually used Kubernetes, my thesis / startup / grad job, whatever, all of that runs on a Kubernetes cluster, which is cool. It lets me do a lot of powerful stuff. But I was saying this before, Kubernetes makes the impossible stuff hard, but doable. It also makes the easy stuff hard. Everything is hard using Kubernetes, but in exchange for that, stuff that would previously be literally impossible to do is now still difficult, but doable. So take this with a grain of salt. It may or may not be actually useful if you try to apply it elsewhere. But how this works. So Kubernetes works with YAML files, right? You give it a YAML file describing what you want it to do, it'll build it. And the base component of all of these YAML files, they're all have a kind, metadata, name, labels, whatever, and then a spec where you describe how to build it. The main kinds of things that you want to build in Kubernetes are pods, deployments, and services, I guess. A pod is basically just a Docker container. A pod is, please run my Docker container with these configurations. So you give it a name, you say I want to run a pod. The image, which Docker image you want to run, Postgres, you can tell it which ports you want exposed for it on the network, you can give it names, all of that sort of stuff. Right? And if you say Kubernetes, please create this YAML file, it'll spin up a pod with Postgres in it. Now, the thing is, pods are decidedly mortal, right? Some pods are literally just temporary jobs that are meant to start, run, and stop. Some, even the ones that are servers, start, run, eventually crash. Kubernetes doesn't restart pods if they die. If the pod dies, and you need to make a new pod. Instead, we have a higher level of abstraction called a deployment or something, which inside of its specification of how to build it, you give it a template, which is the exact same pod config as before, and you say, I want to have 3 replicas of this at all times, or 6 replicas of this at all times. And it will, depending on what you need, create things, delete things. If things die, it'll restart them to make sure that you're always where you want to be. With me so far? Right, the last thing before I stop putting YAML on the screen is labels. You can attach key value labels to any pod, deployment, whatever. What this means is that within command line tools, clusters, tooling, whatever, you can do filter queries, like I want to find all of the pods that do this with these labels on them. Some uses for that would be maybe I want to find all of the pods with this label, because that means that that label is only being applied to my application, and so the load balancer can just load balance out all of the pods with that label on them. Another thing would be monitoring tools. I want you to read the logs files from every pod with this label on it, and so on. There are as many uses of that as you can be bothered thinking up, but YAML on the screen makes a boring presentation, so we're going to stop now. Next up, cool Kubernetes things is auto-scaling. Cue cheesy animation. So I was saying before, you want 3 databases, or you want 6 databases, or you want 12 Java apps, or 1 Nginx. All of these numbers are a little bit arbitrary. I mean, sure, if you have enough data on how many customers you have, how many customers you expect to have tomorrow, what sort of variation you expect and all of that, you can build up a little Excel spreadsheet that says, I need 3 databases tomorrow, or 4 databases over Christmas because more people are visiting my site. Alternatively, you don't do that, and instead, we do auto-scaling. So you start with a random guess of how many you need, and then you have a function or an API endpoint or something that says, what sort of load are we currently under? If we're under too much load, just add more. If we're under not enough load, take some off. And you can do that fully inside of Kubernetes. You can say, I want this deployment to have a variable number of pods based on how many we actually need to meet the traffic requirements. And it'll happen, which is pretty cool, I think. Anyway, what else can we do with all of Kubernetes? So this is just a highlight reel of cool things that I've found over my time Googling these topics. Not all of these relate to Kubernetes. Kubernetes is a pretty undisputed industry leader for open source cluster orchestration, right? If you are Google or Facebook, you have your own internal tools. Apple might have one as well, I think, I don't know. They built their own. We don't get to see those as a closed source. But Kubernetes is industry leader for the free to access ones the open source communities use, or other people like me that don't have the engineering time to write my own cluster orchestration service. But some of these stories are things that I've heard about their internal ones. So anyway, highlight real time. Borgmon, here is Borg from Star Trek. Borg, literally named after that thing, is Google's internal Kubernetes equivalent. They named it that because it takes all of the hardware in a cluster and it just sort of assimilates it into one centralized body that you can use, which is basically, yeah, it's a really cool name. There are a bunch of nerds, and so am I. Anyway, Borgmon is a monitoring tool. So it does all your dashboards, all your metric gathering, all your log parsing and reading, and the big red downhill spike when you cross applications breaking and the email alerts and all that. It's the full thing that's built on top of and very closely around Borg, right? So what it does is it uses Borg to spin up monitoring agents using special internal rules, say for every 100 servers I want one monitoring agent. And then it uses extra rules saying, look at the labels on each of these containers. If it has a label saying, please monitor me, collect monitoring information off of that. If it has more labels saying this is the format that our monitoring information is exposed in, please connect in that particular way. And so you end up with this situation where if you just put your applications on and you just leave notes on them saying this is how this app should be monitored, it'll connect for you, it'll read the data, it'll funnel the data back through all of its layers into the one centralized server that gives you your dashboard that you put in the team office and sends you the phone call at 3 a.m. that you really didn't want, and all of that. But it works on top of the cluster orchestration system, and by integrating with the cluster orchestration system, it's able to do a lot more cool stuff, like all of the labeling stuff, which is pretty neat. That's Borgmon. Next up, also stolen from Google and also internal and also hard to access. And also, I learned about both of these by reading the Google Site Reliability Engineering book. Would recommend. Anyway, Oxon. So this is where stuff gets really cool in my opinion. They added an extra layer on top of their specifications. So it went from, I want to create a Postgres database and a Java application to, I want to create a Postgres I want to create some Postgres databases and some Java applications, such that every Java application is within a 12 nanosecond or millisecond, whatever reasonable numbers are here, is within this network delay of a Postgres server. You look at cluster information, you run some network analytics at the start, you figure out how much lag you have, you set the constraint solver on it. You integrate that inside of your orchestration system, everything just gets better. A little bit of time cost to set things up, of course, but worth it and really cool. All right, next up, this is not an internal Google thing, though Istio kind of is. Service meshes. Google's done a lot in this area, and Google's also the only person in this area that's publishing their work as they go, even if they're not letting us use Borg, but they are talking to us about it at least. Anyway, service meshes are the latest type thing in cluster orchestration. If you think that using Kubernetes makes your easy tasks hard and your impossible tasks possible, and you want to go in that direction of making everything hard, but equally hard regardless of how hard it should be, service meshes are the next step along that path. It makes the easy stuff even harder in exchange for making the really hard stuff also the same level of difficulty as the easy stuff now. Levels the playing field, I guess. So what a service mesh is if you look at all of your pods that are all connecting to each other in all weird ways, it puts a little sidecar on each of them. So a sidecar is a smaller application that runs with your main application in the same namespace and everything. Right? But what it does is it'll intercept and proxy network requests between your pod and the rest of the internet, and it'll just tweak things a little bit as it goes. For example, collecting and collaborating all of the metric data that you need, latency, error rates, all of that, how many 500s, how many 400s, how many 200s. It'll do all of that math for you, aggregate it, send it to the metric server without you having to put that in your code. Things like, if I want to connect to a server and make a HTTP request, it'll notice your outgoing HTTP request, send one of its own. If it fails, it might automate the process of retrying it 2 or 3 times before sending you the error. If it allows you to do smarter load balancing, so on the client side, you look at the central database of which ones are up, which ones are down. You can do your load balancing there and decide what to talk to rather than everyone going through the same big Nginx. On top of that, you can set fancier network rules. You can get pretty graphs saying these pods are talking to these pods this often. All of the stuff. Istio and Linkerd are 2 example service meshes. Istio does a lot more, but is a lot harder to set up unless, this is the one that was made by Google, unless you're using the Google Kubernetes engine, in which case there's a button to just add Istio to your cluster. Linkerd doesn't have as many features, is however free, open source, more easy to use, doesn't come built into Google, but also can be operated by a regular mortal and installed without as much pain, so there's that. Anyway, that's service meshes, they're pretty neat. Final one is Helm. Helm is a pretty big thing in the Kubernetes ecosystem. It's a package manager for clusters, right? So if you think how normally you might say, I want to apt install Vim on my Debian box. Well, I want to Helm install Postgres on my Kubernetes cluster. It keeps all the configuration of this is how many Postgreses we need, this is all of the auto-scaling logic we need, this is the sidecars that we attach to Postgres to do the monitoring and logging, this is the information of, this is the separate job that we run every week to back up the database to S3. It bundles all of that into a single file or into a folder, and you can say Helm install it, Helm delete it, Helm upgrade it, Helm roll it back to a previous upgrade. And they're all just atomic actions that you can do with one command and one tool, which is nicer. The other common thing with this is, as well as using third-party Helm charts, they're called, you can take your application with your list of microservices and how they connect, and you can chuck that into a Helm chart as well. So you can say, in your CD process, continuous deployment, you can say, helm install my application. And then it breaks horribly, and you say, helm, please just go back to the way my application was yesterday. And it'll remember that for you and just put the old config back. At which point Kubernetes will find the difference between the old config and the new config and readjust your cluster so that it works again. Which is pretty neat. Helm, at the moment, I would not recommend using it for another couple months. They are in between version 2 and version 3, and version 3 is going to be so much better than version 2. Version 2 is currently causing me a lot of headaches at my day job. But when Helm 3 comes out, it's going to be great, I hope. At which point it will be definitely worth using. The last, what can you do with Kubernetes? Self-plug is micro. That's my thesis / startup / grad job / whatever else you want to call it. It, for better or worse, all runs on Kubernetes. So there's a couple of microservices, I guess. They all run on a cluster. I can spin up different microservices for different development branches, staging environments, and it's all just on the same 3 VMs, so I get a low cloud bill. It's pretty cool. Talk to me about it afterwards if you're keen. Anyway, does anyone have any questions? That would be it.